This short video is going to look at the product rule. So let's start by just looking at what the product rule is. So the product rule, obviously, we're going to use product. So we're going to have two functions. Here I'm going to use f and g. So when I try to find the derivative of f times g, I'm going to get the derivative of f times g plus f times the derivative of g. Notice we only take the derivative of one of the functions at a time, while the other function remains unchanged. So anytime we have the derivative of a product, we will have a sum of two products as the answer. What I really think is when I'm taking the derivative of a product, I should see my answer get a lot bigger. So let's take some examples so we can see how this works. So I'm going to start us with f of x is 2x times the natural log of x. So I'm going to write this out the long way. We're not going to end up doing this as we go on, but I think as looking at examples, it's good to see what I'm doing. So I'm going to start by taking the derivative of 2x, and that's what I have written here is just 2x prime to say I'll come back later and I'll take the derivative, and then I'll keep ln of x alone. Then I'm going to add 2x stays the same, and I will take the derivative of the natural log. All right, so you should know the derivative of 2x is just 2, and then I keep ln of x as it was. Then plus, because it's always plus with the product rule. I still have my 2x, and the derivative of natural log is 1 over x. So looking at the 2 ln of x, there's nothing I can do with that, but 2x times 1 over x, I could cancel the x's, so I just get 2. So this is my answer. The derivative of f of x is 2x times the natural log of x, ends up being 2 ln of x plus 2. Let's look at some more examples to see how this works as we have different functions. So let's take this function f of x is 9x plus 2 times 7x plus 3. Reality is you could multiply this out, right? You could do FOIL and get a different answer, but we're not going to do that. I want you to see how the product rule works. So notice here, when I go to do the derivative, I'm telling you what I'm going to do. So this is my plan of attack. I'm going to take the derivative of 9x plus 2. I'm going to leave 7x plus 3 alone. Then I'll add to that 9x plus 2 times the derivative of 7x plus 3. Okay, so each time I'm taking the derivative of one of the pieces, and I keep them in order. So the 9x was first. You'll see that first in both cases. It's just the derivative of the first one the first time, derivative of the second time. All right, so 9x plus 2, the derivative is 9. 7x plus 3, nothing happened, plus 9x plus 2, I keep the same, and 7x plus 3, the derivative is 7. Okay, this still looks kind of messy, so I'm going to distribute the 9. So I have 9 times 7x is 63x, 9 times 3 is 27, 9x times 7 is 63x again, and then 2 times 7 is 14. I'm going to gather those two 63x's, which gives me 126, and then 27 and 14 gives me 41. All right, so let's keep going. I picked two more functions, again, that could be multiplied out, but I just want us to see this practice. Eventually, as we go, we will make these bigger. So this 4x squared minus 6 right now doesn't have a power. Later, it's going to. So that's why I want you to practice the product rule with these kinds of functions. All right, so once again, my plan of attack is take the derivative of 4x squared minus 6, leave x squared plus 3 alone, then switch it. 4x squared minus 6 stays. 8x squared plus 3, I'm going to take the derivative. Okay, 4x squared minus 6, derivative is 8x. Nothing happened. 4x squared minus 6, left alone. This derivative, 8x squared plus 3, is 16x. All right, so I think you kind of have two choices right now. You could think, oh, let's multiply this whole thing out. But I want you to start thinking the opposite way. I want you to think, let's factor if we can. So we first want to skim through all of our functions and say, could I simplify this? Because that's where it's going to end up. So it's not a whim of, this time I feel like multiplying, next time I feel like factoring. It should always be, if possible, let's try to factor. All right, so see this 8x here? I have a 16x here, so they both are a multiple of 8. They're both a multiple of x, so you can see that I just took the 8x out. So this 8x, I factored out here. Do you see I still have 8x squared plus 3? Then over here, when I divide by 8x, it would give me 2, and I still have this 4x squared minus 6. Okay. So the 8x squared plus 3 is fine. I want to multiply 2 times 4 is 8, and 2 times 6 is 12. Down here, 8x squared and 8x squared, 16x squared. Positive 3 minus 12 is 9. This is a difference of squares, so if we wanted to, we could keep factoring, and eventually we will. Right now we don't really have any cause to, so this is okay to get it down to this right now and stop. So let's look at another example. I want to throw e in here. So this time I have 3e to the x times x squared plus 4. And again, I'm setting out that I'm going to start with the derivative of 3e to the x, leave x squared plus 4 alone, switch that up, leave 3e to the x alone, and go back and take the derivative of x squared plus 4. So 3e to the x. Derivative is 3e to the x. Remember, e is awesome. It doesn't change, so it should be our easiest derivative. X squared plus 4 stayed the same. And then 3e to the x over here we were keeping. X squared plus 4, the derivative is 2x. So once again, I want to look at it and go, well, what do these two have in common? And I hope it's just really staring at you. There's a 3, here's e to the x, I take that out. And then these three things, x squared, 4, and 2x, I just put together. Nothing factors, nothing cool happens, so we would just stop right there. All right, so here I have an example. I wanted to use another one that we've been talking about, which is, well, two things here. An exponential, so I have 5 to the x, and then I also put with that log base 5 of x, just use 5 for everything. No reason to, I could have different bases, but I thought it would work out nicer. So again, I took the derivative of 5 to the x, or I'm going to, and I left log base 5 of x alone. Then go back to 5 to the x and come back and take the derivative of log base 5 of x. So remember, when we're doing exponentials that are not e, you repeat 5 to the x again, natural log of the base. So I have 5 to the x, natural log of 5, times, there's my log base 5 of x from our original function. Then I keep 5 to the x, and then when I take my derivative of log base 5 of x, remember, logs are always fractions. This x goes in the bottom, and derivative of my base, so I have not derivative of my base, but natural log of my base, so natural log of 5. All right, the only thing I see in common, I have this 5 to the x, I see this 5 to the x. This natural log of 5 and that natural log of 5, really can't mess with those, so leave those alone. Take those 5 to the x's out. I have the natural log of 5. I have times the log base 5 of x, and then plus 1 over x natural log of 5. We really could do a little bit more here if we wanted to. I could convert this over to the natural log of x over the natural log of 5 and end up with ln of x there. I think that'll just kind of freak you out at this point, so we're not going to mess with that right now. I'm just going to say leave it alone for now. We'll get to pretty stuff like that later. For now, I just want to see you doing derivatives, seeing if you know the product rule, along with also your exponential and your e and your log and your ln. You have enough going on without me doing too much to cleaning this up yet. So there's a few examples. I hope that helps out in you trying to learn the product rule.